So the next problem is similar. You have this slightly modified source. Now there's an inductor in series with a resistor, and it goes through a transformer, which then goes to the same type of load as we had in the last problem. And the question is, what should the transformer be? What should the ratio of coils between N1 and N2 be to maximize the power delivery to the load, where the load is defined as to the right of terminals A, B? So this sounds like a very complicated problem, but it's actually, since we solved the previous one, not bad at all. We already know that everything to the right of A and B, that capacitor in parallel with the resistor, has an equivalent impedance of 2.5 minus J 2.5 ohms. And we also know that, well, we need to find out what our impedance is of the inductor. So let's find out what our impedance is of the inductor. That's going to be J omega L, which is J 2 pi 60. There's our omega. Our L is 2 over 3 pi. So that gives us J 80. So now we can rewrite our circuit in the frequency domain. Since the 80 is in series with this inductor, which has a impedance of J80, that's equivalent to a single 80 plus J80 impedance. We've got our inductor. It's not an inductor, rather it's a transformer with the primary coils of N1 and a number of secondary coils of N2. And the load looks like this 2.5 minus J 2.5 load. And the question is, find the ratio of coils defined as the secondary to the primary, N2 over N1, that maximizes the average power dissipated by our load, where this is our load. So we're going to begin exactly as we did for the last problem, getting rid of that transformer by using its Thevenin equivalent. And by using the Thevenin equivalent to the right of these two circles, we, of course, destroy all the internal currents and voltages to the right of those two terminals. But to the left of those two terminals, it looks the same. And you first might say, well, why would we do that? Because we want to try to maximize the power dissipated in this region. And aren't we destroying that power? And the answer is that although we're destroying the internal currents and voltages, if this is an ideal transformer, we have not altered the power that's being dissipated by this, only the currents and the voltages. So this entire circuit still is an accurate representation of how much power is delivered by the source, how much power is absorbed by the source load that's somehow built into the source, the Thevenin equivalent of the source, and how much power is delivered to and absorbed by the load. And now we'll use the rule of maximum power transfer, the maximum power transfer theorem. And that says that if you have a source with a source impedance, the source load that dissipates the maximum power is the same as the complex conjugate of the source impedance. And that's the maximum power transfer theorem. There is more to this theorem. It also says that the maximum power delivered to the load, if you obey this rule that the load is set to the complex conjugate of the source impedance, is going to be equal to the magnitude of the source voltage squared divided by 8 times the real part of Z. And although that's true, we don't need to use that. All we need to use is this highlighted part, because we know that our load impedance, 2.5 minus J 2.5 divided by N squared, it'll appear different as we change around the transformer, has to be equal to the complex conjugate of our source impedance. So that tells us that 2.5 minus J 2.5 over N squared is equal to 80 minus J80. And we can cross multiply and divide through to find that N squared is equal to 2.5 minus J 2.5 all over 80 minus J80. And therefore, N is equal to the square root of this. So N is equal to 0.177. Now, it shouldn't bother you that this is not a simple ratio, because we could, for instance, say that this is equal to our N2 over our N1, but we could make our N1 equal to 1,000 turns, and we could make our N2 equal to 177 turns. So that would completely work to optimize our power delivery. And if we wanted to find out what that maximum power delivery was, even though I didn't ask you, you could just plug it into there.